Good afternoon, everyone. In the previous class, we have discussed until this power equation, the power developed in the rotor, which is PM. PM is equal to 3 into IR dash square into RR dash into 1 minus S by S, where S is the slip. And we have derived this equation in the previous class, which is named as equation 5.8. From this equation, we have know that the torque developed in the motor is a T is equal to P by M, sorry, PM by omega, where PM is the power generated in the rotor and omega is the rotor speed or the motor rotating speed, actual speed of the motor. And that is named as equation 5.9. Now using 5.8, we can substitute PM equation here. And similarly, using equation 5.3, what is 5.3? From the slip, we have derived the actual speed in terms of slip. Synchronous speed into 1 minus slip is 5.3. So we have derived PM and the omega M. Substitute these two equations, which is 5.3 and 5.8, in equation number 9, so that we will get the torque equation as this one. If we simplify, 1 minus S and 1 minus S will get cancelled. So the torque equation, final expression for the torque equation will be T is equal to 3 by omega ms, where omega ms is the synchronous speed, into IR dash square into RR dash by S. But we know what is IR dash square. Equation 5.5 shows the expression for IR dash. So from this equation, substitute this value in equation 10. Substitute here. So this is a square term. That means we need to apply whole square here. So if you get the square here, then this is V square. And in the denominator, we are having a root, and square and root will be cancelled. So the final expression for the torque will be given by equation number 511. So this is the final expression of the torque which will be developed in the induction motor. And you know all these terms, where omega s is the synchronous speed, RR dash is the stator referred rotor resistance, and V is the stator input voltage or stator voltage simply, and RS is the stator resistance, XS is the stator inductance or reactance value, and XR dash is the stator referred rotor reactance. So equation 511 gives us the final expression for the torque developed in the induction motor. Okay, but we need to derive the maximum torque. At which point we can attain the maximum torque for the induction motor. So to derive that maximum torque, we know this relation. See, in order to derive the maximum torque, we need to differentiate the torque and make it to 0, so that we will get the maximum condition of the produced torque or developed torque. So this differentiation can be done with respect to the slip. So d by ds of, this is the torque expression just now we have seen, which is equation 511. So we need to differentiate this equation and make it to 0. And from this equation, write the constant terms outside and other terms which are S terms, because we are differentiating with respect to the S. S means slip. With respect to slip, we are differentiating. So these are the constant terms. Just we kept outside, and d by ds of this entire term. So you can see this is 1 by u and this is v. This s is a derivative, and this entire product will also contains s. So this is s, and here also yes. So the derivative of 1 by u into v. So like that we need to do our derivation or differentiation, sorry, not the derivation, differentiation. So before that, before doing the differentiation, these are the constant terms which is multiplied into this one. Now you can keep these terms, or you can get these terms this side. So 0 by anything will be 0. So we can eliminate simply these terms. So we'll have only this term, differentiation of this entire term. And you know the differentiation rule, 1 by u into v. Use the differentiation rule and simplify the expression. If you apply the differentiation rule, you will get this type of expression, and this is very complex one. You further simplify this expression, you will get like this. And from this expression, solve for s or slip. After differentiation, you will get like this, and again further simplify this expression, you will get this equation. From this equation, you calculate s value. So from this equation, s square will be rr dash square by rs square plus xs plus xr dash whole square. So this is for s square. So apply both sides square root, so that we will get the s value, which is plus or minus, because we are making square root. That means we will get plus or minus. So plus or minus rr dash by square root of rs square plus xs plus xr dash whole square. Name it as equation 512. So this expression gives us the maximum slip that will be allowed for the given motor. So this is the maximum slip that can be allowed. And you can see this maximum slip is a constant for a particular motor after the design. Because rotor resistance, after designing the motor, rotor resistance is constant value. And rotor resistance is also, sorry, stator resistance is also constant value, and XS, XR, all these are constant values. Because once the motor is designed, these are all constant values. Then we know what is the slip will be. So the slip maximum will be calculated with the help of equation 512. And in order to simplify, or in order to get the maximum torque, because we need to attain the maximum torque value, our aim is to attain the maximum torque. Okay, so from equation 512, few terms are rearranged in order to get the maximum torque value. This denominator has been shifted to here, and this s is shifted to here. So we will get this equation 5.13. You can see rr dash by sm. Sm means a slip maximum, or maximum slip you can say, equal to square root of r square plus xs plus xr dash whole square. Now this equation 513 is substituted in equation 511. Why? Because in the equation 511, you can see here in the equation 511, in the place of rr dash, so here we are having rr dash by s, and also here also rr dash by s. We need to replace these two terms, because we need to make the torque independent of the slip. So that's why I'm completely eliminating s term by simply replacing rr dash by s terms here and here. So from equation 513, See, from equation 513, we know RR dash by S is this one. So you can see here that the term is replaced with this term. And similarly, you can also see here that is also replaced. So again, you simplify this. This is a large expression. We need to simplify this again. And after simplification, this will be our final torque expression, which is equation 5.14. And this expression is the maximum torque that can be obtained from a induction motor. And you can see this maximum torque is a function of speed, and it is a function of stator voltage. And you can see it is a squaring function of stator voltage. That means we can directly say if this speed is constant, then torque is directly proportional to voltage square, where V is the stator voltage. So that means with the help of stator voltage, if we can control the torque of the induction motor. So this is how the voltage can be regulated in order to regulate the torque of the induction motor. Okay, so this torque is directly proportional to the square of the voltage. And this expression, equation 514, describes the maximum torque expression. This is the maximum torque expression. And other things are constant here for a given motor, because stator resistance, stator inductance, and stator referred rotor inductance all are constant for the designed motor. Because if a motor is already designed, then we cannot change the windings and all. So these all values are constant, and the synchronous speed is also constant, because 120 F by P for a fixed frequency, the number of poles are constant for a designed motor. So if the frequency is also constant, then synchronous speed is also constant. 3 is a constant value, 2 is a constant value, omega ms is a constant value, and all other parameters are constant. That means the torque or the maximum torque is directly proportional to stator voltage square. So this expression is very much important in order to work with induction motors, particularly for controlling the induction motor with the help of stator voltage. Now we got the expression in terms of stator voltage, which is a squaring, directly proportional to the square. Okay, and this is equation 514, describes maximum torque. Similarly, equation 511 we have already derived for final expression of the torque. See, this is final torque expression. This is final torque expression. However, in this expression, we have slip, because slip is not constant. Slip is a variable term, because slip is always depends upon the speed of the machine. So that is the reason why from using equation 511, from 511, we have derived the maximum torque that can be attained from an induction motor. That equation we have derived using differentiation with respect to slip. So dt by ds must be equal to 0. This is the condition to achieve the maximum torque. So applying this differentiation to the torque value, which is the equation 511, after simplifying, we will get the maximum slip, which is equation 12. Now we are replacing the maximum slip or S term in the actual torque value in order to get the maximum torque. This is the maximum available torque. Sorry. And this expression is further simplified. Sorry. That expression is further simplified, and equation 514 is obtained after all the mathematical simplification. So this equation 514 describes the maximum torque of an induction motor. Thank you.